This video is all about introducing rules to compute or find common derivatives. We'll finish up this video being able to differentiate polynomial functions. The definition of the derivative, which involves taking the limit of the change in a function value as we look at a change in a variable value, is quite tedious to apply when used in full. Fortunately, many of these common derivatives are well known and have been tabulated. They can be shown using the definition of the derivative, but generally we don't bother to go through the whole process. So here we're going to talk about common derivatives such as the derivative of constants, powers of a variable, constant multiples of a function, and sums of different functions. And now in this table you can see we've got a number of functions here, f of x being a constant, f of x to the n, f of x is c, or a constant, times another function u of x, and f of x is the sum of two functions. The derivatives then on the right, a constant becomes 0, x to the n becomes n times x to the n minus 1. The constant just multiplies by the derivative of the original function, and the derivative of a sum of functions is the sum of their individual derivatives. So rather than applying the definition of the derivative, the limit definition, we can use this table of rules whenever we come across these types of functions. So let's have a look at some examples. Here we've got to find the derivative with respect to x for each of the following. First we have a derivative of a constant, then a power of x, a constant multiple of a power of x, and finally the sum of these functions. Pause the video now and try to have a go at these yourself. When you come back you can follow through and see us doing it here on the computer. First up, in A we have f of x equal to the number pi. Now pi is just a constant, so from the top row of the table in the previous slide, the derivative must be equal to 0. So we can just write straight in f dash of x is equal to 0. In B, f of x is equal to x to the 4, or a power of x. Our table tells us that when we have a power of x, we simply bring that power down the front as a multiplier and decrease the power by 1. So here, f dash of x will be equal to 4 times x to the 4 minus 1, or 3. In C, we have f of x equal to 3x to the 5th. Well, this is just a constant multiple, 3, of the function x to the 5th. So f dash of x is going to be equal to 3, because we leave the constant out the front, multiplied by the derivative of x to the 5th, which is 5x to the 4. Cleaning it up, we have 15x to the 4. Finally, in D, f of x is equal to the sum of the three functions we've already differentiated. In the table, it tells us that when we have a derivative of a sum, it's just the sum of the individual derivatives. So we can use our three results of 0, 4x to the 3, and 15x to the 4 to give us that f dash of x is equal to 4x to the 3 plus 15x to the 4. And then we have the first four examples, differentiating common functions. Here, all sorts of constants and multiples of powers of x. Let's have a look at a more applied example. We're told that in every cycle, a piston's displacement, s, in centimeters, as a function of time t in seconds, is given by the function s of t is equal to t cubed minus 6t squared plus 8t. We're asked to find the instantaneous velocity of the piston when t is equal to 2 seconds. If you feel confident, stop the video now and have a go at this one yourself. To answer this question, we need to note that displacement and velocity are related through differentiation. Instantaneous velocity of something is given by the derivative of its displacement function. So to find the instantaneous velocity of the piston, we need to differentiate our function s of t. So the velocity, v of t, will be equal to ds dt, or s dash if you like. And this is just a polynomial. Powers of x, powers of t, all added or subtracted from each other. So we can use the rules that we know to differentiate. We get 3t squared minus 12t plus 8 as our instantaneous velocity at any time. So that would work for any time that we like. On this curve here, we could figure out the instantaneous velocity anytime we wanted. We're particularly asked to figure out the velocity when t equals 2 seconds. To figure that out, we just need to substitute in t equals 2. So we have 3 by 2 squared minus 12 by 2 plus 8. We add all those up and we should get something like minus 4, and it's going to be in units of centimeters per second. Just quickly checking that that makes sense, if we look at the graph, the instantaneous velocity is given by the derivative, and its slope should be, as we can see, negative, minus 4. So it sort of makes sense. It looks like the piston is moving in a negative direction, 4 centimeters per second. Displacement and velocity, as we've just seen, are related through differentiation. Just working again on that example of the piston, we found that for our cubic displacement function, we got a quadratic or second degree polynomial velocity function. We can plot both of those on the graph at the same time. So the piston's displacement is given by the solid line, and its velocity given by the dashed line. And the point that we found it was down here at minus 4 centimeters per second. Graphing these two functions in this way allows us to see some interesting relationships about our piston, or whatever it was that we could have been applying or modeling with those functions. If we look over at the right hand picture, I've shaded in some pieces in green and some pieces in red. So you'll see that the pieces I've shaded in green, between time equals 0 and time just a little bit less than 1 second, our velocity function is positive, so the piston is moving upwards. Then when we move into the red section, from here to here, somewhere between just less than 1 second and just more than 3 seconds, the piston's moving downwards, and you can see that the velocity function is always negative in this region. Then again we pass back up again, the piston's moving back upwards, and our velocity function is positive. So we can see all sorts of different relationships by investigating our derivatives and seeing how they relate to the original functions. So to summarize this video, we now have fairly easy to apply rules, much easier than the definition of the derivative, that allow us to differentiate constants, powers of a variable, constant multiples of functions, and sums of functions. Basically, we can now differentiate polynomials.